The topic today is adversarial search. Earlier in the class, we spent some time looking at search algorithms as they can be applied to state space problems. And in those problems, we were assuming that the only factor that could change the state of the environment were the actions that the agent was taking. That assumption goes out the window if there's an adversary, right? So if we're playing a game, for example, against an opponent, it's harder to make plans involving long sequences of actions because we don't know how our adversary is going to respond to the actions that we take. So I'm going to use the terminology games, and that's the standard terminology in this area. But of course, we can construe the idea of games quite broadly. Games could be tic-tac-toe, they could be chess, or a global thermonuclear war. So anytime that we're making decisions in the face of some adversary, we're going to think of that as a game. So in a game, we make decisions, and then our opponent makes decisions, and we alternate. So what do we do about making a plan, given that we don't know what our opponent is going to do? Well, one possibility might be to just choose an action that seems reasonable on some basis, wait to see what the opponent does, and then respond to that action without thinking ahead very much. That won't get us very far. Even in a game like tic-tac-toe, we have to have a plan that goes a few steps into the future in order to guarantee that we can win. So in order to make progress here, we're going to have to make some assumptions about the actions that our opponent will take when we're choosing our own actions. And one reasonable way of making assumptions is to assume that our opponent is as clever as he could possibly be, or as she could possibly be. So we're going to assume that we're playing against an optimal component, or an optimal opponent. When we make a decision, our opponent will always make the decision that is as bad as possible for us. So let's look for a second at how we might represent these games. Let me bring up an example from the book. Here's a game. It's a sharing game that's presented as an example in the book. And here we have two players, Andy and Barb. There's some resource that they're distributing between themselves. Maybe it's $2. Andy has to decide whether he wants to. He's proposing some way of distributing this resource to Barb. So he's saying, well, he has three choices. He can suggest that he keep all the money. He can suggest that he shares the money evenly, or he can suggest that he'll just give the money to Barb. No matter which of those options Andy chooses, Barb has the choice of either accepting, saying yes to that allocation, or saying no to that allocation. If she ever says no to a particular allocation, the money disappears and no one gets it. If she ever says yes, then the distribution that Andy suggested goes through. So we can think of this as a game, and these numbers at the end represent the outcomes for the different paths through this game tree, right? So a particular instance of playing the game might start with Andy suggesting that he wants to share, Barb saying no, and then neither of them gets any money. I'm going to modify this game just a little bit to get into the spirit of sort of zero-sum adversarial games. So let's assume now for a second that we're not really thinking about sharing, we're thinking about winning, right? So in this case, and we're going to think about it from Andy's perspective. So what I want to do is put a single number at the end of each of these, at each of these leaves, indicating how good that outcome is from the point of view of Andy. And that's how we'll think of these adversarial search algorithms. We'll be thinking from the perspective of a particular player. So in this case, Andy gets all of the money, so obviously he's happy with that, so we'll just call that a +2 outcome. In this case, he gets no money. He suggested that he should keep it all, and Barb said no. Well, that's kind of what he expected. That's a 0 outcome. Now, from this point of view, Andy's reasonably happy. He got $1. But let's look at this possibility. So here, Andy suggested that the money be shared. Barb said, no, I'll take nothing and you'll get nothing. Oh, that hurts his feelings. So that's a -1 outcome for Andy, because that was just a mean thing for Barb to do. And then finally, we've got this give outcome where Andy just proposes, all right, Barb, I'll give you all of the money. So in this case, right? This is a 0 outcome for him. She takes the money. He doesn't get any. And here, he's really emotionally damaged because he offered to give her money and she said no. So this is how we can think of this as an adversarial game. And if it's adversarial, right, both players are trying to win. So not only is Andy trying to get the best possible outcome for him, but we're going to make the assumption that Barb is trying to get the worst possible outcome for Andy. So I said that this was a zero-sum game. So right from this, at this leaf, Andy has a +2 outcome. We could then view this as a -2 outcome for Barb because she's really sad that Andy came out so well. Maybe this isn't the most friendly example, but it gets into the spirit of these adversarial games. Okay, well, how can we think about choosing a strategy here? I've already said that Andy's strategy is going to be to assume that Barb will always do the optimal thing from Barb's perspective. So whatever choice that Andy makes, he's going to assume that Barb is going to pick the outcome that's best for her and worst for him. And that leads directly to an algorithm. So this is the Minimax algorithm. This isn't explicitly presented in our book. There's something called alpha-beta pruning, which is going to be a way to make this algorithm potentially run more efficiently. So what I've done is I've just stripped out the alpha-beta pruning bit that would make this more efficient to just get the basic Minimax algorithm in front of us. And, well, there's a lot here. You'll have to spend some time looking through it on your own. But I'll point out that it's a recursive algorithm. So every time, right, so this is an algorithm for calculating the value of a particular node in a game tree from the perspective of Max. So traditionally, these players would not be called Andy and Barb. We might call them Max and Min. Max is trying to maximize his outcome at the end of the game, and Min is trying to minimize his outcome at the end of the game. So all of these nodes are either Max nodes or Min nodes. Decisions that Max makes are Max nodes. Decisions that Min makes are Min nodes. So what does this algorithm do? It takes in a particular node in the tree, and it returns the value of that node from the point of view of Max. So our goal is to assign a value to every possible position in this tree, every possible state in this tree, which corresponds to some point in the game, and decide how good is it to be at that point in the game from the perspective of Max. And then obviously he'll choose actions that try to make his position in the tree as good as possible. So it's a recursive algorithm. If we are at a Max node, we're trying to decide how good that node is for Max. What we'll do is, at that point, we need to know for all of the children of that node, what's their value, right? And their value is going to be determined by how bad Min can make the value of that node. But Max gets to choose which of those children will happen, right? Because we're looking at a Max node. So the value of a node is the maximum of the value of all of the children. Similarly, if we're calculating a Min node, right, this is where Min gets to choose. So Min's choice is going to be based on the value of all of the children node from that point onward. And the value of those will be based on what Max does. But when Min makes this choice, Min will choose the value that has the smallest, that is worst for Max. So this is a recursive algorithm that pops back and forth between calculating Min nodes and Max nodes. And we could probably worthwhile to step through this algorithm on this simple example. It's a recursive algorithm, so it's initially called with this root node as n. That root node is not a leaf, so we don't return that value, right? These values only actually come into existence when we reach one of the leaves. It is a Max node, so we're going to, so now we have a loop that's going to calculate the min, the value of all of the children here. And this is going to be a depth-first recursive algorithm, so first we're going to call Minimax on this first child. We'll get back to the top of the algorithm, so now we're at this point in the algorithm. It's not a leaf, it's not a max node, it's a min node. So now we need to iterate over all of the children of this node. So there are 2 children, and they're both leaf nodes, so they'll both return the value associated with that node. So this will be +2, +2, this will be 0. And since we're calculating a min node, the actual final value associated with this node will be 0. So now we popped back up recursively to the calculation that we're making to calculate the value of the max node. We've finished that first child, we move on to the second child, the process will be the same. So this 1 will come up, this -1 will come up. The value of this node is -1, and similarly the value of this node will be -2. So at that point, Max gets to decide what the value of the node that's being calculated is. He'll look across all of these possibilities. It's the max of 0, -1, and -2. So the value of the root node is 0. And so we've implicitly decided on a course of action. Let me rewrite these things in green so we can see what we're talking about. 0, 0, -1, -2. So those are the calculated values that this Minimax algorithm has given us. So now we know exactly what's going to happen when this game is played, given that the Minimax assumption of optimal play holds. Max will choose the keep alternative because it has the highest value among the 3 alternatives that he has, 0, -1, and -2. Min will then choose the no alternative because that has the highest value, or the lowest value among these alternatives, +2 or 0. So the optimal play for Max is to say that I'm going to keep everything and then be turned down. That's kind of a sad story, but that's the way this game works out.